Okay, so 3 questions. You're going to have to identify the type and solve. Right? And then we'll go through them. Right? You can mark your own. Be honest with yourself when you mark it. Okay? I'm not taking it in, but you need to be able to look at that and go, okay, I don't know how to tell the difference between this question and that question. That's something I need to focus on this weekend. Okay? Everybody with me on that? All right. Here are your 3 questions then. So, what kind of question is number 1? Yeah, it's a work question. It's a work energy theorem question. What's the dead giveaway? It gives you the work, and it uses the word work in the question. Okay. Now, obviously, on the unit exam, I'm probably not going to be that straightforward. Question might include force, distance, okay, and of course only have a change in either potential or kinetic energy. Okay. What kind of questions are the other 2? They're both conservation of energy. Now the third one, while mathematically identical to all the ones we've done so far, is contextually a little bit different. And sometimes that throws people. But we'll get to question 3 in a little bit here. We'll just pull those out of the way for now and work on question number 1. Okay, so a load of construction materials has a mass of 350 kilograms. Okay, and it is lifted from a height of 10 meters above the ground. Okay, so that would be my what? Initial height, because it's lifted from there. To an unknown height, okay, using 1.37 times 10 to the 5 joules of useful work. Is it okay that I put that in scientific notation? Can you guys enter things in scientific notation into your calculator? And that's all you have to do here. It's just like Avogadro's number. All right. That's a terrible J. It's not anything like a J. Joules. That's better. All right. So I've got that. I'm looking for the final height of the load of construction materials. Okay. We've already established that this is a work question. What kind of energy is changing? Potential. Potential, because it's talking about height. Okay. So delta EP. All right. Exactly what you're going to have to do on the test on Monday. Identify what kind of question, what kind of energy. All right, and this one I don't have to put FD over here because I was told the work, which makes it a little bit easier. But I still have to do this. EP final minus EP initial. I'm looking for final height, which is part of which term? EP final, right, part of this. So how do I get that by itself? Add EP initial over to the other side. Okay, so my change in energy plus my initial potential energy should equal my final potential energy. That logically makes sense. So, all right, now I got to put in my formulas. So work plus M times G times H initial equals M times G times H final. All right, something I need to remember about these that I can't do here, but I can do in a conservation of energy question. What can't I do here?
Wipe out the mass.
Yeah, I can't just wipe out the masses here. Mass is not part of this term. Therefore, it is not in every term, and thus I cannot cancel it. So just because sometimes people over-apply that, this doesn't work here. All right, so I need to find H final. What do I do with M and G? Divide them over to the other side. That, again, does not cancel the M and G on the top. There's an addition-subtraction operation on the top. All right, so if I plug in my numbers, I'm going to have 1.37 times 10 to the 5 joules, okay, plus 350 times 9.81 times 10 meters, divided by 350 times 9.81. All right, so in brackets, 1.37 E5, okay, plus 350 times 9.81 times 10. Okay, and then divide that by 350 times 9.81. All right, so the final height of this thing is going to be 49.9 meters. All right, so this would be a 5-mark question on your test. You get one for your givens. You get one for work energy theorem. You'd probably get one for isolating, one for your algebra, and one for your answer. 5 marks. Okay. Questions on number 1? Okay, how are people feeling about work energy theorem? All right, second question, bobsledder question, which is really about as cut and dry for a conservation of energy question as you can get, right? We said like sledding and stuff like that is always a conservation of energy situation because there's no mention of friction, there's no mention of work or forces or anything like that. Okay, so we can assume that for this bobsledder, okay, that the energy between point A and point B is the same. So when he is 45 meters above the end of the track, that would be his initial height. He is moving at 12 meters per second. That would be his initial speed because if you've ever watched bobsled, they push the sled really hard for like the first 10, 15 meters and then they jump inside. Okay? Then they go down the hill. How high above the bottom, that would be my final height, are they when they are moving at 23 meters per second? So I'd give you a mark for your givens there, okay, picture or whatever. We've already said there's no mention of work, no mention of force. We can assume then that this is an isolated system and all of the energy will be conserved between top and bottom. All right, so I would have EP initial plus EK initial equals EP final plus EK final. All right, in this question, are any of those zero? Not in this question. I mean, we have to assume the final height is probably not zero, okay? Given that this is a 45 meter high hill and this is not a heck, I mean, yeah, it seems like a lot faster, but to go down that far is not, okay? So, we can't cancel any of those off. None of them are zero. What I'm looking for is final height, which is part of that term. How do I get that by itself? All right, subtract EKF over to the other side. All right, so we've got initial potential plus initial kinetic minus final kinetic equals final potential. All right, so do I need to put my numbers in now? Or my formulas, sorry, not my numbers. Time for that? Yeah, HF's not on the board yet, so I got to get it in there. So M times G times H initial plus 1/2 MV initial squared minus 1/2 MV final squared equals M times G times H final. What can I do with all the M's in this question? I can cancel them here. It's in every single term, so that can go away. All right, what do I do with the G? Divide this G over to the other side so that I can isolate my final height. All right, now this would be a 6-mark question. So as I said, you get 1 for your givens, you get 1 for conservation of energy, you get 1 for like your isolation, 1 for your manipulation. What are we up to there? 4. Okay, 1 for plugging in your numbers. So that would be 9.81 times 45 plus 1/2 times 12 squared minus 1/2 times 23 squared divided by 9.81. Okay, so that would be your 5th mark, and then your 6th mark in this question would be for your answer. So 9.81 times 45 plus 0.5 times 12 squared minus 0.5 times 23 squared divided by 9.81. All right, so they will be moving at, or sorry, they will be 25.4 meters above the bottom. And that would be your 6th and final mark on that question. Okay, questions on number 2? I mean, that's like basically every conservation of energy question we've done where you had to solve for height. Okay. Now, is it possible on the unit exam, maybe I give you one where one of those forms of energy is 0? It's possible. I could be talking about like the very top of something where they're not moving, or I could be talking about the very bottom where their height would be 0. Okay. It's possible I could do that. It does make your algebra a little easier because you usually have one less thing to move around. Okay. All right. Question number 3 sometimes throws people. It's a conservation of energy question, but this object is doing something no other object in a conservation of energy question we've done is doing. What is it? Yeah. This is the first one we've had where the object was moving up the hill at the beginning. In every other question we've done, the object was moving down a hill. Does it make any difference? This is why I put this question on there. It makes no difference because direction doesn't matter. Energy is scalar. In these questions, is there ever an arrow over top of the V? It's because you have kinetic energy regardless of which direction you are going. Up the hill, down the hill, doesn't matter. Okay? You've got this amount of speed, you've got this amount of kinetic energy. All right? Direction makes no difference. But it kind of throws people sometimes because they're like, what? It's going up the hill? It's going to slow down. Yes, good, you do understand it. It is going to slow down. It's going to slow down and lose kinetic energy because its height is going to get bigger. Yeah. Okay? And in actual fact, if we're talking about this car going up the hill, okay, if the top of the hill is up here, eventually this car is going to come to a what? Stop. And then it's going to roll back down the hill. In fact, it will pass this point twice. Will it be going the same speed when it gets to that point? Up and down? It has to, because it has the same amount of mechanical energy at that point, whether it's going up the hill or down the hill. It's run out of gas. The engine's not doing any work anymore. That's the key to this question. Okay? So you're going up the hill and all of a sudden, boom, the car runs out of gas. Well, it's going to roll and then it's going to go back down the hill. Okay? When you pass that point the second time, same speed, just different direction. Direction doesn't matter. Okay? It's energy scalar. That's the whole point of this question. In terms of solving this question as an energy conservation question, it's exactly the same as all the others we've done that solve for speed. Okay? So, as we've already spoiled, it is a conservation of energy question. Our givens are that we start down here at an initial height of 10 meters, moving at a speed of 25 meters per second. And a little while later, we are up here, okay, at 18 meters at an unknown speed. Okay, so any of our forms of energy zero here? Not likely. I mean, it's possible that this could be the turnaround point and the speed could be zero, but I've never made you solve for one where that was the case because it's kind of mean. Okay, so I wouldn't do that. Spoiler alert tomorrow. Okay, or on Monday, I mean. Okay, so we've got EK initial plus EP initial equals EK final plus EP final, right? What I'm looking for is part of EK final. I want to know the final speed of the car, right? So what do I have to do with EP final? Subtract it over to the other side. All right, so I'll have kinetic initial plus potential initial minus potential final equals kinetic final. All right, now I can put in my numbers, or sorry, my formulas. 1/2 mv initial squared plus mgh initial minus mgh final equals 1/2 mv final squared. M's all cancel. Okay, we don't require any of those. I need to get VF squared by itself. What do we do with the half? Divide it over to the other side. Okay, and I want VF, not VF squared, so square root. Okay, same as we've done on every other energy question where we solve for V. All right, so now I need to put in my numbers here. So VF will be, okay, 9.81 times 10 plus 1/2 times 25 squared minus 9.81 times 18 divided by 1/2 all square rooted. Okay, so 98.1, I'm just going to put that in there. Okay, plus 0.5 times 25 squared minus 9.81 times 18 divided by 1/2 square rooted. Okay, does that answer make sense in terms of the context of the question? We started out at 25, now we're going 21.6. Yeah, we're slowing down because we're going uphill. Okay, so that answer makes sense within the context of the question. 21.6 meters per second. So that would be your sixth and final mark. You'd get a mark here for your number plugging. You'd get a number for your manipulation. Okay, number here, there, and givens. I think that's 6 marks for that one. Questions on that?
Did it do 22? Is that?
Yeah, just show all your work and I'll know where that answer comes from and then you'll be fine. Okay? All right, any other questions on it? Okay, so unit exam on Monday. You're gonna get one like this, okay? It's either gonna solve for height or speed, that's all we ever do before. Okay, you're gonna get 2 work energy theorem problems. Okay, one for potential, one for kinetic. Okay, the trick is make sure you can tell them apart. Right, you know the patterns, follow the patterns, you can't really go wrong. Show all your work. Okay, in case you mess up on the calculator, show all your work. And then you'll have some acceleration problems, some graphing problems, okay, all the things we've gone over in this unit. We'll talk more about that tomorrow when we do the unit exam review in its entirety. Remember that I did post a unit exam review package already, okay, that you can be working on. I would suggest getting started on that sooner rather than Sunday night. Okay, Sunday night would be a very bad time to start doing that. I mean, it's better than nothing, but it's also really late. Okay. All right, let's move on to efficiency then. All right, I'll give you a couple minutes here just to find that lesson in your notes, okay, and then we'll skip. Okay, so efficiency is the last thing in this unit, okay? It is probably right up there with V equals D over T in terms of the easiest math you have to do in this unit. Because when it comes right down to it, efficiency is a percentage measure of how much energy got put into a job compared to how much energy actually got, or how much work actually got done, right? Because in an isolated system, those two numbers would be equal because no energy would be lost during the job. It would just be 100% converted. Well, nothing works that way in the real world, okay? So you calculate efficiency in exactly the same way you calculate what your percentage is on a test or a quiz. You take what you got and you divide it by the possible points to get, and you get 100%. Well, okay, maybe not every time, but right, you know what I'm talking about. You get like 0.85, you know, or 0.95 or whatever. Okay, 0.95 is how many percent? 95%. Okay, that's all we're going to be doing with efficiency. Okay, is we're going to have an energy input. That's how much energy gets put in. We're going to have a useful work output. That's how much work actually got done. Divide the top number by the bottom number. You've got your percentage. Top number is always going to be bigger or smaller? Smaller, has to be. Okay? If you ever do one of these questions and you get 1.15, you've either discovered something critical to the development of our society and you will be filthy rich and save the world, or you messed up the math somewhere. I'm thinking it's probably the latter, but I would really hope for the former. Okay? So just so you know, if you ever get a number that says more than 100%, you did something wrong, because getting more than 100% efficiency is impossible. Okay? All right, so efficiency is super important in our society. We want to be good stewards of our resources. Okay? We don't want to waste things. Okay? So we're trying to make things more and more efficient. That is, get that number closer to 100%. Okay, it can never be 100%, but you know, we want to get as close as possible. What do you suppose is a good number for efficiency? Like, what would you accept? Now, if you had a machine that was doing a job, what would you want it to be at? 99. Yeah, you'd want to be as close to 100 as possible. Would you accept something that's less than 50? Okay, most people shake their heads no at that, what you do every day. If you get in a car that has an internal combustion engine, you accept something that runs at somewhere between 16 and 25% efficiency. To put that in real world, make you cry kind of numbers, if you put $100 worth of gas in your car, only $18 to $25 of that $125 actually propels the car forward. Okay? $65 of that is wasted completely and does no useful work. Okay? It makes me sad every time I take my truck to the gas station and I sit there holding up the line while it goes chug-a-lug, 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 chug-a-lug for like 10 minutes. Okay, well, the 137 liter fuel cell fills up. Okay, yeah, it's very sad. Okay, but I can't, yeah. You trade efficiency sometimes for other things. So what we're going to look at here is some places in our, everyday life. Specifically, we'll look at cars and light bulbs and things like that. Okay, where we've improved efficiency. Okay, if we take two identical vehicles, like two identical models. Okay, I'm going to use our newest car. Okay, as kind of an example here. A year and a half ago, we bought a Lincoln Corsair plug-in hybrid. Okay, because we wanted to make better use of our resources. So you can buy a Lincoln Corsair that's just an internal combustion engine. Okay, so just gasoline versus the hybrid vehicle. Okay, so they're the same size, same wheels, tires, mass, the whole works. Okay, so if I'm driving the just internal combustion engine, just gasoline engine car, okay, I'm driving that along, engine losses. Okay, this is not energy driving the car forward. This is losses. Okay, 68 to 72%. Right? That means 68 to 72 dollars of your precious $100 of gas that you put in the car are going to thermal energy loss from the radiator, exhaust heat, that's just the hot gases coming out the tailpipe, okay? And then the heat you can feel if you're standing at the front of the car when the fan is blowing, the radiator is blowing that heat away, okay? That's 58 to 62%. Combustion, about 3% loss, okay? Pumping, that's actually like the water pump that circulates the coolant, that if it didn't do that, your car would melt down and destroy itself. Okay, that's 4%. And then internal friction is another 3%. Okay, that's a lot of percents, and your car hasn't moved forward yet. Okay, the reason for that is internal combustion tries to convert heat or thermal energy directly into mechanical energy. On like the second day of this unit, we said that's like the least efficient thing you can do, is try and turn thermal energy into mechanical energy. But that's what your car does. Okay? When the fuel goes into the cylinder, so I don't know how familiar you guys are with how a car's engine works. Inside a car's engine are pistons. They're round things that look like kind of a pop can. They go up and down inside a cylinder that is about the same size as they are. Right? They go up and down 4 times in one cycle. That's why a car's engine is referred to as a 4-stroke engine. Okay, so the first stroke of the engine is actually the piston moving down. Okay, when the piston moves down, it pulls the air-fuel mixture in to the cylinder. Okay, the second stroke is the piston moving back up. And what it's doing in that part is compression. This is a compression stroke. So there's the intake stroke, then there's the compression stroke. So the engine piston is moving up, and it is compressing the air-fuel mixture. That is making it more volatile, okay, because it's compressed. When it gets to the top of the compression stroke, the little spark plug at the top of the cylinder sparks and ignites this highly compressed mixture of air and fuel. That causes a small explosion. That explosion results in hot gas being produced, which then expands because hot stuff takes up more space than cool stuff. Okay? That is turning thermal energy, the heat from the explosion, directly into mechanical energy. Those expanding gases push the piston down. That's called the power stroke, because that's the only one of the 4 strokes that actually produces power. Okay, so it pushes the cylinder down, or the piston down in the cylinder, and then the piston returns, but on its way up, instead of compressing the fuel, one of the valves opens and all the exhaust gases come out. That's the exhaust strokes, 4 strokes. Okay, only one of those strokes actually produces power, called the power stroke. Okay, so all of that is going on. That heat that's produced, very little of it ends up pushing the cylinder down. The rest of it has to be pulled away from the engine so the engine doesn't destroy itself. Because what do things do when they get hot? They expand. Okay? Well, if you've got a metal pop can, like piston, moving inside of a metal cylinder, and both of those get hot, they both expand, which means they actually squeeze on each other. The piston expands outwards, the cylinder expands inwards. The hotter your car's engine gets, the less efficient it becomes, because there's more friction. It's why you want to keep an eye on your temperature gauge. Okay? If the temperature of your car gets too high, you need to stop and let the car cool off. You've probably run out of coolant, or there's something else wrong with your car. Maybe your oil should have been changed ages ago, okay, or something along those lines. It's not good for your car to run at high temperatures. It gets less efficient because the piston grinds on the inside of the cylinder a lot more. Similarly, it's why you need to have your car properly lubricated. Change your oil regularly. Use good oil. Okay, all of that kind of stuff. Because without it, the engine will get too hot. If the engine gets too hot, your car will seize. That is, the expansion of those metal parts will get so bad that the power generated by exploding gas will not be sufficient to move the cylinder up and down anymore. When that happens, or the pistons are up and down anymore, when that happens, usually metal parts begin to break. Connecting rods and things like that that are, trying to drive your car, they snap, okay? Or the piston just goes through the cylinder wall. Either one of those is a loud, catastrophic expensive end to your car. Okay? You do not want to have either one of those happen. So you got to watch out for temperature. Okay? Why do you have to watch out for temperature? Because your car is ridiculously inefficient. But that's what we got. So that's what we drive. Okay? Other things that your car does that are inefficient. There's auxiliary electrical losses in your car. Lots of things in your car run on electricity. Okay? The door locks, and if you have like heated seats, okay, or you have the rear window defogger, those little lines of the grid that runs across your back window, that runs on electricity. It's like a dead short that just heats up the window really quick. Okay, fan, okay, headlights. If you've got like a big car stereo, okay, like the guy that drives by my house, he's always playing the same song. Maybe you guys know it. It's always the same song. I don't know what it is, but he's always playing the same one. Okay, and his car must like register on the Richter scale. Okay, but he's got to have probably a second alternator. The alternator is the part of the car that makes electricity. There's a belt that runs off of your main drive shaft that powers your water pump, your alternator, so the thing that makes electricity, all of that. If you have like a huge stereo, 6 giant subs in the back, like 4 amplifiers, okay, you probably need an extra alternator to make enough electricity for that. That would increase this auxiliary electrical losses, right? So that would be climate control, fans, seat, steering wheel warmers, headlights, all that kind of stuff. Okay, then you have parasitic losses. That's water, fuel, oil pumps, ignition systems, pollution control, engine control systems. All that stuff takes heat. Okay, heat goes in there and it's lost. Okay, energy to the wheels, 16 to 25%. That's what propels your car forward. So the precious $100 worth of gas that you put in your car, $16 to $25 actually ends up turning the wheels. Okay, is that really good? Well, it's a heck of a lot better than it used to be. Okay, 16 would have been the top end of that number 20 years ago. Okay, cars were even less efficient then. Okay, we're actually pretty fortunate in that internal combustion engines have become a lot more efficient, okay, in the last 10, 15 years than they were before that. Okay, you also have other drivetrain losses, 3 to 5%. Okay, that's just if you've got, the axles there, the transmission, things like that are turning the wheels, there's friction there. Okay, and then idle losses. If you have an internal combustion engine and you have to stop at a stoplight, your engine keeps running. Unless, and this is one of the modern advances in cars, lots of cars actually, when they detect you've stopped moving forwards, they turn the engine off. Okay, so your car actually isn't running at the stoplight, and then when you press the gas, the starter fires up, starts the engine, and off you go. Okay, I hate that. I've driven a few cars that do that, and they all have a setting where you can disable it, because I just hate pressing the gas and nothing happens, and then they hear the starter go, and then the car goes. It's just annoying. I'm old school. Okay, so idle losses. I'm one of the 3% idle loss people. Okay, now that's internal combustion. Okay, strictly that's all this car runs on is gas. Okay? Your other option is to have a gasoline electric hybrid vehicle, okay, which still has an internal combustion engine that runs on gas. But it also has a battery and an electric motor. These are really good if you're in commuter style stop and go traffic. This is where they really shine and where they allow us to get the most efficiency. Because if I accelerate in a gas-powered car, that's when I use the most gas. Okay, during acceleration, when I'm trying to do work and change my energy, that's when I use the most fuel. Agreed? When I'm cruising along on the highway, my car doesn't have to work as hard. Okay, that's why internal combustion engines get really good highway mileage, but really bad city mileage. Okay. Hybrid cars are the opposite. Okay. Hybrid cars get decent fuel economy on the highway, but they get great fuel economy in the city. Because every time I press down on the gas to accelerate, the gasoline engine starts to go, but the electric motor turns on as well. So it helps the internal combustion engine. Okay? This enables you to put a smaller gasoline engine in, okay, which would use less fuel anyway, and the electric motor helps that engine. So it doesn't have to work as hard and use as much fuel. Everybody kind of follow me there? Okay, so you've got an electrical system that helps. Okay, that's all in a true hybrid, that's all it does, is it helps to power the car along, which makes it more efficient. Okay, and it usually is best when the car has to work hard. So if you're going up a steep hill or you're accelerating away from a stoplight. Okay, so if we look at the numbers here, engine losses goes down from 68 to 72 down to 65 to 69. There's some overlap there, but it's a little bit better. Okay, it's still the same things because you still have an internal combustion engine, but it's a little smaller. Okay. Then you've got your parasitic losses. Well, those are the same. You still have water, fuel, oil pumps, ignition systems because you still have an internal combustion engine. So those numbers are the same. Your auxiliary electrical losses are actually a little greater because you have a few more things that run on electricity in a hybrid car. Okay? Your drivetrain losses, okay, they're about the same, 3 to 5%. You still have a transmission, you still have, all that stuff. Energy to the wheels, 24 to 38. So if all of these are close, why is this number suddenly so much bigger? Here, regenerative braking. Okay? In electric vehicles and in hybrid vehicles, remember we talked about the first day of this unit, we talked about the thermocouple, the thing that turns heat directly into electricity. Those are built into the brake rotors of a hybrid car or an electric car. Every time you press on the brakes in a regular gasoline-powered vehicle, all the heat that's produced is completely wasted. It's just gone. It goes out as thermal loss to the surroundings. That's what your brakes are supposed to do. Turn it into thermal energy that can be dissipated so you slow down. In a hybrid car, some of that energy gets converted back into electricity and goes back to the battery, which can then extend your range because now your battery is charging itself. Okay? The battery charges itself anyway while you're driving. The alternator charges the battery as well. Okay? But braking gives you some of that energy back. Energy that in an internal combustion engine would just be lost. Okay? And it gives you back anywhere between 5 and 9%. Well, right there, that accounts for going from 16 to 24 or from 25 to 38. Okay? You get a lot more energy to the wheels because you get energy from the battery, which makes you more efficient, and you get the battery charging itself. Okay, using up energy that would otherwise be wasted. Yeah. All right. So we recently, a year and a half ago, bought, like I said, a plug-in hybrid. So it works essentially like this, except it actually has two batteries. It has a hybrid system battery that works like what I just explained, and it also has a pure electric car battery. Right? Now, if we're driving just with the hybrid stuff on, the main electric battery is already dead, okay, then we're driving like this. And we get way better fuel economy than we got in the vehicle we replaced. Okay? Vehicle we replaced in the city, we were lucky if we got like 10 liters per 100 kilometers. Okay? When we're driving in this car in the city, we can get 3.2. Okay? Because that electric battery, that electric motor is kicking in and making sure that the gas motor doesn't have to work as hard. On the highway, there's barely any improvement because that's not the part where the engine works hard. Okay? Our other car got about 7.5, we get about 7. Okay? It's a little bit smaller, that probably accounts for it. Okay? A hybrid car, you're getting what you want if you're using it in stop and go traffic. If you're just going to drive on the highway, it's not necessarily going to do what you want. Okay? Are you reducing your carbon footprint a little bit with this car? A little bit. You got to think about where the battery comes from and how they harvest all that material, okay, and all the energy and stuff that gets put into building the battery and stuff. There's actually a fairly large carbon footprint for making a battery. But yeah, over the life of the car, you're using less gas. So you're putting less CO2 in the atmosphere. And it costs way less money to run on electricity than it does on gas, okay? This we know as well because our car can run on pure electricity from the separate battery. Okay? Now, it's not a lot. We can go in the summertime 52 kilometers on just the electric battery. Charging that electric battery costs us just over $1 in electricity. To go that distance in fuel would cost us $3.25. Okay? And we bomb around town on all electric all the time. That's why we bought the car. Okay? So we could just drive around all the time using just the electric motor. Okay? And it saves us a lot of money. Now, is that good? Heck yeah. I love pulling that thing up to the gas station every 6 weeks and putting $35 worth of gas in it. Okay? Unlike pulling my truck up to the gas station every 2 weeks and putting $138 worth of gas in it if I'm only at half a tank. Okay, so yes, makes you shiver. Okay, but that's what you do, right? You have some things that run efficiently, some that don't, right? But we're making better use of the input fuel if we're having something that runs more efficiently. Okay, and we do the same thing with light bulbs. Okay, if you buy like the tungsten filament incandescent style light bulb, okay, and you screw it into the socket, it's 60 watts. That means it uses 60 joules of electricity per second. Most of that is heat. Okay, the tungsten bulbs, they just got hot. Okay, that's how they made light. The tungsten doesn't conduct electricity very well, so when you force electricity through it, it just gets really hot and it glows and it makes light. Well, we can replace those now with a 4-watt LED bulb. Okay? We can be 15 times more efficient with an LED bulb. Okay? Is it smart to do that? It makes a huge difference on your electricity bill. If you switch out from one to the other, man, your electricity usage just goes right down. Okay? So we do that because it's more efficient. Okay? It's better use of resources. I'm still getting the same amount of lumens, that's the light, but I'm using 15 times less energy. Okay? All right, what about an electric car? Is that going to be more efficient? Way more efficient. Electric motors are highly efficient because they don't have a lot of parts that rub together. There's very little friction. Plus, they don't use heat to make mechanical energy. They use electricity to make mechanical energy. Okay? That is way, way, way more efficient. Okay? So if I look at this example here with the electric car, okay, energy to the wheels, 87 to 91% when you factor in the regenerative braking. Okay? The internal combustion engine was like 68. Okay? That's way, way better. Now, there are still some losses. When you're charging the battery, there's some heat produced. Okay? I know this because when I plug in my electric car at home, okay, I can actually hear this coolant pump that's running that circulates coolant past the battery as it charges to keep it cool. Okay? So there's 10% loss there. You still got your same accessories, your heated steering wheel, heated seats, power windows, power door locks, that's 3%. The electric drive system still loses 18%, but it's not 65% that's being lost, it's 18. Okay? There's electrical losses, 4%. Okay? So yeah, 65 to 69% to the wheels, but you get to add on that regenerative braking. And in most electric cars, there's a thing called a brake coach that tells you how good your braking is and how much of the energy possible is going back into the battery. If you stomp on the brakes and skid to a stop, it's going to read like 10%. Okay? But if you slow down slowly and let that heat build up and let it turn into electricity, it gives me 100% if I do well, and it's a game. If I'm driving my wife's car, and it's a game always. Ask my boys when we're in the car, and I look over the thing, yeah, every single time they get so annoyed. Yes. And then I get like one where I stomped on it, I only get 65. Okay. All right, is that making some sense? Now, am I saving myself money by going to this car? At least in fuel. I'm saving 100% in fuel, not putting any in. Okay? But I'm still paying the electric bill, right? But I don't use nearly as much electricity to drive to work in an electric car as I do gas to go to work. Okay? It's less efficient. I would spend more money. Right? Now, are you reducing your carbon footprint by having an electric car? A bit. I mean, it is more efficient, so in that way you are reducing your carbon footprint. But where does most of our electricity come from? Oil, coal, natural gas. Okay? Yes, we have those solar farms that they're putting up everywhere. Yes, we have the wind turbines down by Pincher Creek. Those amount to less than 10% of the total input to the power grid. So you're still burning fossil fuels to power your electric car. Okay? Unless you're like the people in my neighborhood. There's a whole bunch of them that have done this. They got the solar panels on their house, and then they wired that directly into their electric car charger. So they went out and spent $100,000 to get solar panels and an electric car, okay, so that they could save a little bit of. It takes a while for that to pay itself back, but eventually it will. Okay, then yes, you're certainly reducing your carbon footprint. You're charging your car using the sun. Okay? Yeah, that works, but you got to commit to spending a lot of money. In the end, then, does the money I spent in fuel offset the amount of money I spent to put solar panels on my house and buy an electric car? Okay? Yeah, you just got to, sometimes they sell you on, oh, you're doing so much for the environment by buying this electric car. You are doing some things for the environment, but depending on where your electricity comes from, yes or no, right? If you live in Ontario where much of the electricity is produced with hydroelectric and nuclear, well, yes, then you are reducing your carbon footprint, okay? You just have to look at where does your electricity come from. Okay, everybody all right with that idea? Okay, we can always find ways to make things more efficient, and that's good. Yes. Okay, so let's look at how this formula, how does the math of this work? Okay, well, efficiency is just a percentage. Okay, so the formula looks like this. Efficiency is the useful work the machine does divided by the energy it had to put in. Okay, we sometimes call that useful work output, or we call mechanical energy output. That's the top number. Okay, mechanical energy input, or just energy input, is the bottom number. Okay, the bottom number will always be bigger than the top number. Okay, so input is what you put in. That's the number on the bottom. Output is the number on the top. That's what the machine actually does. Okay, when you do this calculation, remember, okay, there's this times 100 part. I don't ever include that in there because I figure, you know what, you guys can probably do that in your head. You know when you see this number come out of that calculation, the percentage is what? 75%. Okay? All right. So let's have a look at an example here. Let's say we're looking at this one with the crane. Okay, so a crane lifts this load of construction materials from the ground to the second floor of a building. In the process, the crane does 2.3 times 10 to the 4 joules of work, or mechanical energy input, while doing 8.00 times 10 to the 3 joules of useful work, or mechanical energy output. Okay, which one of those numbers is the one that goes in the bottom? The first one. Because A, it's bigger. And B, it specifically said this was the energy input. Okay, that's how much energy went into the machine. Right, so that's EI. Okay, and it's 2.3 times 10 to the 4 joules, or 23,000 joules. Right? The 8.0, that's only 8,000 joules. 8.0 times 10 to the 3. That's the useful work output. Okay? 8.00 times 10 to the 3, the smaller of the numbers. Right? We're looking for what's the efficiency. Okay? Well, the efficiency formula, and this one is on your formula sheet, okay, is useful work divided by energy input. 8.00 times 10 to the 3 divided by 2.3 times 10 to the 4. Okay? And like I said, you guys can punch those numbers into your calculator. You know how to do scientific notation that way. Okay, so it comes out to 0.3478, so that's 34.8% efficiency. Everybody all right with that? Okay? That formula works just like V equals D over T. I could give you the percentage efficiency and ask you, and then also give you the energy input and ask you how much useful work was done. You just manipulate for W, okay? Or I could give you the percentage and W and ask how much energy you had to put in. You just have to solve for EI, okay? Easy algebra for you guys at this point. It's just a matter of manipulating this equation for any one part of it, just like V equals D over T. Okay? All right. I'm going to put 3 questions like this up there on the board that I want you guys to try eventually. Okay, I would like you guys to do 1, 2, and 3. Okay, so tomorrow, okay, we'll do the full unit exam review. Okay, sorry I forgot to record the solutions. The solutions are there. Okay, so we'll go over what's on the test, how many questions, all of that kind of stuff. Okay, so you know what to expect for Monday. What do you need to bring with you for Monday's test? A calculator. Okay, you must have a calculator. You cannot use your phone. Your phone will be in a bin at the front of my room. Okay, let's just have a seat, please. Okay, so make sure you have a working calculator. Okay, beg, borrow, creatively acquire. Okay, a calculator for Monday. I have now only 2 loaners. If you are the 3rd person needing a calculator, you are so out of luck. Okay, I don't want that for you. So please bring a calculator for Monday. And pencils, plural, I would say are better than pens on this test because you have a lot less paragraph writing than you did on Unit 2, okay, and a lot more problem solving, and then obviously the multiple choice needs to be in pencil as well. Okay, so make sure you've got that for Monday. You're getting a fresh formula sheet. Don't worry if you've lost yours. Okay, the front page of the exam has the formulas on it. Okay, so you will not be allowed to use your formula sheet because I don't know how much you've written on it. Yeah, so make sure you're ready for that stuff. Remember that I will let you write into lunch hour a little bit should you need the extra time. If you normally write in learning support, I took the test there yesterday, please go straight there for your exam. Questions? All right, so be here tomorrow ready to do the unit exam review. A good way to get the most out of that is to do a little review of your own tonight. Okay? Then you know what kind of questions you need to ask. All right, good job today, guys.